Hello, I am Subhendu Behra. I'm going to talk about our research, P-checkpoint coordinated prioritized checkpointing. First, we'll begin with some background on fault tolerance, specifically checkpoint restart. Then we discuss the motivation behind our research. Then I define the problem statement and describe the proposed solution, followed by the system model and its validation. Finally, I discuss the evaluation of our study and its results. Modern HPC systems features scale higher compared to their predecessors as we make progress with extreme heterogeneity and complex design. We need this to support complex workflows such as simulations, multi-physics applications, advanced data analytics, and machine learning guidance. With this, we expect a lot of failures on these systems, not only a higher number of failures, but also at a higher rate in the order of hours or less. As we can see, for some of the HPC systems, the mean time between failures lie within a few hours. Over the years, researchers have developed many effective solutions, such as redundancy, where duplicate tasks are scheduled to prevent long tail latency and job failures. However, the caveat is that we waste a lot of resources. Then we have algorithm based fault tolerance for applications that can adapt and recover from failures itself, but with limited application. Finally, checkpoint restart, a common technique used in the HPC community to store application state periodically to recover when a failure happens. Checkpoint restart 2 incurs many overheads. Recomputation overhead is the waste of computation that could not be saved because of an unexpected failure. Recovery overhead follows recomputation overhead. Checkpoint overhead is the duration of storing the application state or checkpoint data to a storage medium. Checkpoint restart's efficiency is defined by these different overheads, and there are many factors that can impact the efficiency of checkpoint restart. Some of them are the runtime of a job, the failure rate on the system, the latency gap between computation and I/O, and the degree of parallelism. The longer the runtime of a job, the higher the checkpoint overhead. More failures incur more recomputation and recovery overhead. The higher the latency gap between computation and I/O, the more time spent in checkpointing. Increasing the degree of parallelism introduces more contention for common storage medium like a parallel file system, leading to more checkpoint overhead. Researchers have developed multiple approaches to counter such inefficiencies. For example, better hardware and code reduce the runtime of a job. Failure prediction helps reducing loss of computation due to failures. Finally, multi-level storage solutions reduce the checkpoint overhead due to latency gap and parallelism. Our research focuses on the failure avoidance through prediction. Over the years, there have been a lot of progress in failure prediction on large-scale systems. For example, ELSA uses signal processing and data mining techniques on system logs to predict failures and their locations. This applies deep learning techniques to system logs to predict lead times to failures along with their locations. ROE is a lightweight predictor of failures with lead time and location using deep learning and compiler techniques. As we made progress in failure prediction, there were some significant contributions on failure averse tolerance solutions, such as process level migration using health monitoring. Then we had just in time safeguard checkpointing in coordination with checkpoint restart to minimize the impact of failures based on a statistical failure model. Our previous work combined checkpoint restart and live migration to combat the issue of failures using the ASUS failure prediction model. Despite the significant progress made in failure prediction and failure aware solutions, there are certain failures that still cannot be handled in checkpoint restart even with failure prediction assistance. For that, we analyzed system logs from 3 different real-world HPC systems over a period of 6 months and constructed failure chains using the Desh model. A failure chain is a common sequence of phrases in logs that may lead to a failure. In the figure on the right, you see 10 different types of failures along with their counts on the x-axis. On the y-axis, you have box plots of their lead time distributions. We observe that many failures lead time lie within a few seconds. For example, failure 6, 7, 8, and many more. Next, we look at the variability of IO completion time on Summit supercomputer for individual ranks at scale. As we see, the IO completion time has a long tail latency for various combinations of rank sizes and write sizes. That means an effective fault tolerant solution needs to guarantee enough lead time for vulnerable nodes during just-in-time safeguard checkpoints in face of a failure prediction. Based on these observations, we conclude that adequate lead times to failure are key to success of failure-aware checkpoint restart solutions, and we propose the hypothesis that prioritization of vulnerable nodes in just-in-time checkpoints in a coordinated manner can benefit checkpoint restart models in performance to tackle the challenge of short lead times and unpredictable nature of I/O on modern SPC systems during failures. The idea behind our solution is fairly simple. We prioritize vulnerable nodes checkpoints to the parallel file systems ahead of the healthy nodes for just-in-time checkpoints. We call this method p-checkpoint. To prioritize vulnerable nodes, we apply coordination among processes within an application using node local priority queues. The node local priority queues help us maintain checkpoint order. The vulnerable nodes have higher priority based on the predicted lead time to failures. This provides them low latency on the critical path to the parallel file system. Further, we integrate live migration with p-checkpoint because of its cost effectiveness and continuous execution during the migration process compared to p-checkpoint, which blocks the application during its progress. Live migration also helps reducing checkpoint frequency because of the reduced failure rate, as live migration assisted failure handling avoids failures, whereas p-checkpoint's failure handling does not avoid failures and requires recovery. On the right, you see the state diagram of a node during failure prediction and recovery. When a failure prediction occurs, a node transitions from the normal state of execution to a vulnerable state, and decision is made on the proactive action choice based on the available lead time. If P checkpoint is the choice of action, then a P checkpoint notification is sent to the healthy nodes who transition to waiting mode. Once the P checkpoint is complete, the vulnerable nodes broadcast the PFS commit notification so that the healthy nodes complete their checkpoint to the parallel file system. If live migration is under progress and another failure with lesser lead time is predicted that can only be handled with P checkpoint, then live migration is aborted and P checkpoint process begins. We also assume that live migration transfer size is 3 times the checkpoint size. Consider a stencil with temporal domain of t-1, t, and t+1. For live migration, all three values are needed to be transmitted to the healthy node, whereas a checkpoint requires only one since others can be recalculated. This approximates the overhead for live migration, assuming that these data structures dominate the memory consumption of an application. To summarize our contributions, we propose a novel checkpointing technique to allow vulnerable nodes to commit data in a prioritized manner with application level coordination. We integrate p-checkpoint and live migration, which are driven by Desh's log-based failure analysis and prediction model. Further, we assess the impact of lead time variability, analyze the performance of our solutions along with others. We also provide an analytical model on the impact of checkpoint size. To validate our proposed solutions, we developed various models. The SPC system model is based on a modern SPC system like Summit that has local burst buffers and a parallel file system. We assume that a fault predictor like Arrowhe runs on each node with minimal impact on other applications, and a set of reserved nodes are available for replacement with a faulty node. Our solution differentiates between different types of checkpointing used. For example, the periodic checkpoint commits to local burst buffers first, and checkpoints are drained to the parallel file system asynchronously. Whereas for proactive checkpoints, the checkpoint data is committed to the parallel file system directly, bypassing the burst buffers. So when a failure recovery is performed, the recovery mode depends on if the failure was handled by P checkpoint or not. If it was, then all nodes, including the replacement node, recover from the parallel file system. If the failure was not handled, then all the nodes except the replacement node recovers from the burst buffers. And we use Young's checkpoint formula for the periodic checkpoints. The aim of the I/O performance model is to realize the approximate bandwidth achieved by an application. The bandwidth is used to determine the latency during checkpointing to the parallel file system. First, we find out the optimal number of processes that achieve the best I/O bandwidth on a single node. The figure on the left represents the aggregate bandwidth achieved on a single node for various combinations of process size and transfer size. We found that 8 processes on a node achieve the maximum I/O bandwidth. Then we perform weak scaling on I/O bandwidth by increasing the number of nodes for a particular data transfer size. The resulted performance matrix on the right is used for the latency calculations in our simulation. To evaluate our proposed solutions, we built a simulation framework that integrates various validation models such as the system model, the checkpoint restart model, the IO model, and the failure analysis and prediction model. We request the viewers to refer to the paper for these models. With our simulation framework, we simulate various events such as computation, checkpointing, proactive actions, and failures. Our simulation framework is built using the SymPy Python library, a process-based discrete event simulation framework. Our evaluation is based on the Summit supercomputer. We use the applications evaluated in various previous works for a different supercomputer, Titan. But we scale up the checkpoint size and scale down the number of nodes for Summit based on the system configuration differences between Summit and Titan. For failures, we consider 3 different distributions from 3 HPC systems. We assume that Titan's failure distribution applies to Summit since neither Summit's failure analysis nor system logs were available at the time of evaluation. For comparison, we use checkpoint overhead and recomputation overhead as metrics. Recovery overhead is negligible. We constructed various checkpoint restart models. The base model has only the periodic checkpoint and burst buffers for assistance. Previous works such as safeguard checkpointing and live migration integrated checkpoint restart, denoted by M1 and M2 respectively, have the assistance of failure prediction. Our contribution model P checkpoint, denoted by P1, has the assistance of the advanced method P checkpoint as a replacement of safeguard checkpointing. Model P2 is the live migration integrated model. First, we tested the previous works models M1 and M2 against the lead time variability. The figures on the right have the lead time variations on x-axis and various types of overhead reductions compared to the base model on the y-axis. The higher the y value, the better the savings made by the model. As you can see, model M1, that is safeguard checkpointing, does not provide any benefits for large applications such as Chimera and XCC, as the reduction lines hovers near zero regardless of the lead time change. For M2, the live migration model, the benefits disappear when the lead time decreases by 10% or more. With our contributed models P1 and P2, the recomputation overhead reduction benefits lasts even when the lead times decrease by 50%. The assistance of P checkpoint allows the vulnerable nodes checkpoint to be saved ahead of the failure, thus reducing the recomputation overhead even for the low lead time failures. We only show the results for the large applications. For detailed evaluation, we request the viewers to refer to our full paper. Model P2 utilizes both P checkpoint and live migration. To measure the impact of live migration and P checkpoint, we plotted the difference of FT ratio of LM and P checkpoint in model P2. The FT ratio is the ratio of successful failure mitigations to the total number of failures. On x-axis, we have the lead time variations in the range of plus 90% to minus 90%. On the y-axis, we have the FT ratio difference. We observe that P checkpoint becomes more effective for large applications compared to the live migration for its low FT latency. We also observe that higher lead times favor live migration since this has higher priority over P checkpoint. However, when the lead times are low, P checkpoint takes over. Here we compare the reductions for each type of overhead for all the models. In the figure on the right, we have the applications on the x-axis and the overhead percentage of the base model on the y-axis. Each bar for an application represents a model, and the bar is broken into parts for recomputation, recovery, and checkpoint overhead. The base model is capped at 100%. The lower the bar size, the better the result. We observe that P2 yields maximum overhead reductions between 53 to 65% compared to the previous models with 31 to 61 and 0 to 52% reductions. We also want to point out that both models M1, M2, and P2 provide checkpoint overhead reductions because of reduced checkpoint frequency with live migration. We also assess the impact of reduced failure rate with integration of live migration. Because of the reduced failure rate with live migration, the increase in checkpoint interval leads to higher losses for non-handled failures. This is evident by the fact that P2 yields less recomputation overhead reductions than P1. So we make the recommendations that larger applications with short running time should be using P1, that is P checkpoint, whereas applications with longer running time should use P2, that is P checkpoint and live migration. Here's the benefits of checkpoint overhead reduction compensate for the additional recomputation overhead over a period of time. To validate the robustness of our solution, we tested against two more failure distributions from different HPC systems. We observed similar pattern of overhead reductions for other systems, even though the overall overhead reductions may vary. To assess the impact of the checkpoint size, we varied the live migration size as a factor of checkpoint size. In our previous evaluations, the live migration size was 3 times the checkpoint size. Here, we vary the factor from 1 to 4. In the figure on the right, we have overhead percentage reduction of the base model on x-axis and the applications on y-axis. Each application has models P1 and multiple variants of model M2 determined by the factor of live migration size. Here we compare the models P1 and M2. We observe that the larger the checkpoint or application size, the larger the advantage of P checkpoint over live migration. As P checkpoint performs better for Chimera and XCC, but not for POP, which is a small application. We observe we also observe that P checkpoint performs better than live migration, that is M2, when live migration size is greater than the checkpoint size for Chimera, and when live migration size is greater than 2.5 multiples of checkpoint size for XCC. For smaller applications, live migration always performs better than the P checkpoint. In this section, we derive an analytical model that compares P checkpoint and live migration by taking three different factors into account. These factors are the percentage of failures mitigated by P checkpoint, that is beta, the percentage of failures mitigated by live migration, that is sigma, and the ratio of live migration size to checkpoint size, that is alpha. For P checkpoint to be better than live migration, equation 1 must be true, that says the reduction in checkpoint overhead because of live migration is less than the difference between recomputation overhead reduction by P checkpoint and live migration. Equation 2 represents the relationship between checkpoint overhead reduction by live migration compared with the checkpoint overhead with base model using the percentage overhead percentage of failures mitigated. We assume a uniform distribution of lead times and an equal parallel file system checkpoint latency for a single node and the internode network latency. then equation 1 can be rewritten as equation 3, and if recomputation overhead is equal to the checkpoint overhead, then equation 4 stands true. By using another constraint that the addition of checkpoint and recomputation overhead reductions due to live migration must be less than the recomputation overhead in the base model, we can derive that the percentage of failures handled by live migration must be less than 0.61, and the ratio between the live migration transfer size and the checkpoint size must be between 1.04 and 1.3, which is represented by the figure on the right. To summarize, we developed and evaluated a novel checkpointing method, priority-based coordinated checkpoint, to address the challenges of low lead times and I/O variability. We integrated live migration for its cost effectiveness. The integrated model is driven by the DESH failure analysis and prediction model, where checkpointing decision is based on the lead time to failure, which is used as a priority. We also demonstrate that our solution can provide better tolerance against low lead times and I/O variability and provides better reductions in overhead than existing solutions. We also provide an analytical model comparing p checkpoint and live migration. For more details, please refer to our paper.